This is part two of the videos on Newman projections. In this video, we're going to talk about how to compare the energies of the staggered and eclipsed states, and then also go through some terms like anti, gauche, and sin to discuss what those mean in regards to conformational states of different Newman projections. All right, and then we're also going to talk about how to calculate the total energy that the different interactions contribute to the stability of the conformer. All right, so first let's discuss the staggered versus eclipsed conformations. So let's say that we have this molecule, and we'll use this molecule throughout this entire video. So we have one bromopropane. So if we were to draw the Newman projection down this middle bond right here, we would have that bromine going up, that methyl group in the back going down, and then we have hydrogens like this. And so based off of our video, the previous video, we know that this groups, the bromine and the methyl groups are on opposite sides of that middle bond. We can see that the bromine and the methyl group in this state are opposite each other. We can also see that there's nothing eclipsed. There's no bonds that are directly overlaid with each other. And so this state is considered to be staggered, meaning that the groups are not directly overlaying with each other. However, if we rotate around this bond to create this structure here, where now we take that other side of the methyl group and point it up instead, now we can see that that methyl and the bromine are on the same side of that middle bond. And so if we were to draw a Newman projection for this, that front carbon didn't change. So we still have bromine, hydrogen, hydrogen. But now that back methyl group is overlaid with that bromine. And we are now in an eclipsed state. And so in an eclipsed state, we have additional repulsion energies. So for example, this bromine and this methyl have what's called torsional strain. And so torsional strain occurs between the electrons within those bonds. And so if we look at this structure over here, the actual strain occurs between those electrons in these bonds here. And so whenever we have groups that are directly overlaid with each other, we end up with having torsional strain. So these two hydrogens also have torsional strain. And same thing with this other pair of hydrogens here. And so all together, this molecule has torsional strain between the bromine and the methyl, the two hydrogen pairs, and the third hydrogen pair, or second hydrogen pair, I should say. And so because there's that strain or that clash of electrons, this structure is considered higher energy. And even though we have free rotation around that single bond, because this is higher energy, it's not as stable or not as preferred. And so this state occurs less commonly. And based off the energy differences, you can actually calculate the percentage of the time that the molecule spends in this state. In comparison to that, in the staggered state, we have all the groups are opposite each other. We don't have that torsional strain because those electrons are not lined up with each other. So for example, this bromine and this hydrogen do not have torsional strain. And that's because those electrons are not directly lined up with each other. There's kind of like an angle between the electrons that are found in those bonds. All right, so that's torsional strain. So far we've compared these two structures for just torsional strain. I'm going to move this down because now we're going to talk about steric strain. All right, so in the staggered and eclipsed states, we have torsional strain in the eclipsed state, and then we can also have steric strain. And so steric strain occurs when there are big groups. So for example, methyl groups, butyl groups, just really anything that's has multiple atoms on it. The groups also cause steric strain. And so for example, this bromine and this methyl group end up having clashing occur between the groups because they're bigger, or specifically that methyl group is pretty big. Hydrogens are too small to really have any steric strain, so generally that group doesn't really come close enough in three-dimensional space to the other atom to cause any sort of additional strain, so we don't have to worry about steric strain for those. We can also get steric strain in a staggered state if the groups are big enough. And so, for example, let's say that we had this structure here, where we keep the bromine in that top position, but then rotate the molecule so that we're now in a staggered state, but we're in a different staggered state than that first one. And because that methyl group isn't directly opposite this bromine now, they're next to each other. And so in this state, this methyl group is big enough to have steric strain here too. And so we don't have torsional strain in the structure, but we do have that steric strain that contributes to the energy of that state being a little bit higher than this top one over here. All right. So that's kind of a rundown of some of the differences between staggered and eclipsed states and the energies that contribute to that. We'll look at how to calculate the actual energies for a full molecule in the last part of this video. But first, let's go through the differences between these terms. So you might, in one of your classes, you might be asked to label different states as anti, gauche, or syn. So let's quickly redraw some of those states from above to help illustrate the difference. So we'll start with that first state that we had where the methyl and the bromine were opposite each other. We can also draw the one where the bromine and the methyl were directly overlaid with each other. And then we can also draw that third state where the bromine and the methyl were slightly offset with each other. But they weren't they were still in the staggered state, but not completely opposite each other. And so each of these terms, each of these structures can be used to, can be described using these terms. So in this one, we have this bromine and the methyl are anti because they're opposite each other. Because in the staggered state, if they're directly across from each other, those two groups are considered anti. If they're directly overlaid, then they would be syn. So we only use syn when we're describing eclipsed structures because they have to be directly aligned with each other. And so if you're asked to draw or describe the interaction or like the term that would be used to describe the orientation of the two groups, you have to make sure that it's in the eclipse state if you're using that syn term. And then same thing for anti, we would want to make sure that it's in the staggered state. And anti specifically when they're like directly opposite each other. All right, the last term that we can use is gauche. So gauche is when we have a 60 degrees difference between two groups. So it's usually, or it's used to describe the staggered state also, but when they're not directly opposite each other, but when they're like 60 degrees. And then we could also technically use the same term to describe something like this methyl and this hydrogen, that they're also gauche to each other because they're 60 degrees apart. All right. And so the anti-conformer, when the two biggest groups are anti to each other, this is the lowest energy conformer. And then the opposite is true for the syn. When we have the two biggest groups syn to each other, this is the highest energy conformer. And then the gauche ones is it's just a term used to describe the relative orientation of two groups. So you don't really, it can correspond to really any intermediate values that you would get. All right, so let's use these terms to now compare the energies of conformations. And so again, we're going to use that same molecule that we have already been using. And here what I did was I provided a table that describes the different energies of interactions. And so what you'll notice is that these are all categorized as either gauche or eclipsed. And so when we're calculating the energies, we have to consider the relative orientation of the two groups to determine which correct energy we should be using. Also, just in general, as a heads up, this table is given to us in units of kilojoules per mole. Another really common unit is kcal per mole. So if you're solving a problem for your course, just make sure you have the right units, and it might not necessarily match the numbers that you would get from other sources because they might be using a different energy or energy unit. But okay, so let's start with this one. So first we're going to start off with taking our structure up here and filling in this first molecule. And so this is just exactly what we've done before. And so now we can take this molecule and calculate the contributions to the energy. And so for this, what we'll do, and I'm actually going to copy this over to here just so we have a little bit more space to work with this. So here, we're going to look at the different types of energies that we have. So we can see that we have a bromine and a hydrogen gauche interaction. And so based off of our table, we would want to find where we have bromine and hydrogen gauche interactions. And we can see that these contribute 0 to the energy. Hydrogen, bromine are too small to have any sort of steric hindrance or strain. And we know that we don't have torsional strain because we're in that staggered conformation. And so we don't have to be worried about those gauche interactions. And so there's no contribution from that. We can also take a look at this methyl group. So methyl and hydrogens, if we look at the table here, we can also see that these are gauche. And based off the table, we can also see that it's a contribution of 0. And then hydrogens in the gauche conformation, which are here. Are also 0. And so none of these interactions are contributing any additional energy to the state. And so the total difference from the lowest state is going to be 0 kilojoules per mole. Because we've got 0 plus 0 plus 0. And so this is going to be our lowest energy state. And so if we were to start drawing out an energy diagram, we can place our 0 degrees. So this is just our starting state. And our energy would be 0 here. All right. Next, what we're going to do is we're going to rotate our molecule by 60, or that angle, the carbon-carbon bond, by 60 degrees. And so now we're going to be in this state over here. So we took we are going to keep this front carbon the same, bromine, hydrogen, hydrogen. And we're going to take that back carbon and rotate it by 60 degrees. And so now our hydrogen is pointed up, and that methyl group is to the left instead of being down. And so now we can take this and calculate, do the same interactions that we had done in the previous one. But now what we can see is that we don't have any gauche interactions, and now we have only eclipse interactions. And so for this bromine hydrogen eclipsed interaction here, we can go to our table and we can see that the bromine hydrogen eclipse is 7. And so again, we're using that 7 because we have eclipsed instead of gauche interactions. Next, we can do the same thing for this hydrogen, hydrogen. And the methyl and the hydrogen. And we can see that respectively, those will give 4 and 6. And so now our total is going to be 7 plus 4 plus 6, which would give us a total of plus 17 kilojoules per mole. All right, and so for that 60, our energy state at 70 or at 60 degrees rotation would be at 17 kilojoules per mole. All right, and so then we can just keep going. We're going to take our structure, rotate it another 60 degrees. So again, we're keeping that front carbon the same, but just shifting over the atoms in the back by 1. And then going through the same motions where we go through and just calculate each of those interactions. And so here, I recommend pausing the video and just kind of working through the rest of these states and just working on kind of filling in those energies and calculating them and just making sure that yours match up with what I'll get at the end of this diagram. Otherwise, I'll just walk through it here. So first we want to, for this one, take our interactions here. So we have a bromine and a hydrogen gauche interaction. And this will give us a contribution of plus 0. Next, we have a methyl and a bromine interaction here. And that's gauche also. And so we would want to use that plus 4 value from the table at the bottom. And then we know that hydrogen methyls gauche and hydrogen hydrogens gauche don't have any interactions because they're too small. And so we have a total of 4 kilojoules per mole contribution here. And so if we go back to our table here or our diagram, we would have 120 and then 4 at the bottom here. All right, next we can do 180. So we'll rotate another. I'm just going to start moving some of these up here just so we can organize this a bit better. All right, so in this state, we're going to end up with that bromine and the methyl directly on top of each other in an eclipse state. And so based off this table, this is the highest energy contribution of 13. And then we also have those hydrogens here and here. And so those will end up being +4 each. And so the total across all of these interactions is going to be 21. So we can see that this state is much higher than that previous one. And we get our highest energy that we've gotten so far up here. Next, we can keep going with our last two states, and these are going to end up being pretty similar to the ones that we've already calculated because we have multiple hydrogens. Here we have bromine, methyl, HH. And what we'll see is that the interactions that we get are going to match the states that we got up here. And you can go through and calculate, like identify all the interactions just to confirm that here. All right, so now we can go back and draw in those two energies also. So we have, once we rotated to 240, we end up with 4 kilojoules, then 300, which is that last state ends up being back to 17. And then if we do a full rotation, so if we ended up with like a full 360, we end up back at 0. I'm not going to draw that out, but that's exactly identical to the starting state that we've had. All right, so now we can connect all of our dots. And in general, there are like methods that people could use to like calculate the the individual points, but we can just kind of assume that it's like this wavy pattern here. And what's important to note is that these peaks are all eclipse states. And that one in the middle is like the global maximum. That's like the worst state for this molecule to be in. And then all of these in the bottom are going to be the staggered states. And so we can see that all the staggered states end up being lower than the eclipse states. And you should see kind of that wavy pattern going from the eclipse to the staggered ones. All right, the last thing I'm going to do is just label what each degree is, just so you can match them with the drawing down there. And yeah, so that's what we get. We can draw that energy diagram. And so what this shows is that all of those eclipse states are higher energy states, meaning that they're not as preferred as the staggered state conformation. And that we get less strain, less negative interactions within the staggered states. All right, with that, this wraps up this video. Based off this, you should be ready to complete the Newman projection practice problems. And then when you're done with those, you can take a look at the solution video for those.